Okay, we'll see about that. Uh, we'll see. Yeah. All right. Very quickly, and I'm actually also going to try to take, try to go faster than I've been going. I've been going really slow, I feel. I'm already, I think, behind a lecture, at least from the usual schedule. But if you're sort of having difficulties following the material, I urge you to, of course, read the book and use my notes as a supplement to the book. My notes are by no means complete by themselves. And since the video lectures should be available online, if you're having trouble, go back and take a look at those. I'm also thinking about holding Friday review sessions for those of you who might be really struggling with the material. Okay, good. So we'll do Friday evenings, 5:30, probably right here in this room. I'll check room availability and all that, and I'll send out an announcement. And I think the focus of those review sessions would be pretty much to go and address some very basic things, not really look at your homework problems or some of the trickier problems, but very basic things. Absolutely, everybody should be able to do in the class. Okay. All right. So with that, let me very quickly recap where we were last time. We've been talking about this calculus of scalars, vectors, and tensors. We looked at two types of derivatives for the scalar fields. One was a directional derivative for scalar fields. Then we looked at a gradient of a scalar field. For example, if we have a scalar field that looks something like this that you can plot in terms of contours, we saw that the gradient measures how it changes in different directions, and we got that the gradient of a scalar field is a vector field. So these were the two types of derivatives for scalar fields. We looked at vector fields, which, as I pointed out, the way to visualize a vector field is that you are given a space. It could be some solid or it could be a structure, and in every point of the space or every point of the structure, you have some vector associated with it. So it could be a flow field, or if you think about structures, it could be a displacement field. Right? So if you have a cantilever beam or a building, then when it deflects, you can plot the displacement of each and every point between the initial undeformed and the final deformed configurations. That's a displacement field over the entire structure. So that's what a velocity field would look like. And last time we looked at three types of derivatives of this velocity field. A divergence, which we said that if we define a delta operator something like this, which is just taking derivatives with respect to x1, x2, and x3, then we can write the divergence of any vector field as the dot product of this operator, this derivative operator, times the dot product of the derivative operator with the vector field itself. I also pointed out that a more consistent way of writing it is v dot grad rather than grad dot v, but I'll come to that. In either case, it shouldn't matter. Dot product is symmetric. I will also point out that writing the grad operator in this form and calling it a vector, is this a vector, this grad operator? Does it have some magnitude and does it have some direction? That's what a vector is, right? A vector has magnitude and direction. So indeed, this grad operator, it's not really a real vector. So when I write it in the form of a vector, it's abuse of notation, no doubt about it. But it helps to write it in this form so that we just so that we can make our calculations easy. Okay. So another thing to point out about the initial notation, we are going to be using commas to denote derivatives. And I should write here it is partial of partial with respect to xi. All right, so then we looked at curl of a vector field, which is circulation around a point. So, and indeed, when we defined it, we said it would be minus of grad cross product with the vector field. or more consistently, vector field cross with the grad product. Both of them would be equal. And finally, we looked at the gradient of a vector field, which, as I said, would produce a tensor field. So we had a gradient of a scalar field, which produced a vector field. If you take the gradient of that vector field, you'll get a tensor field. Okay? And we looked at this example of the vector field of X that produced a tensor field of identity. And the way to visualize that would be using the same example that we've been looking at previously. If you look at this scalar field that I gave you, scalar field, x dot x, we took the gradient of that scalar field and we got 2x, right? So that scalar field on the base that looks like these concentric circles of different colors, of glowing colors, that's basically what a scalar field looks like in 2D, which is what I've plotted here also. So if you look at the circles, they go from blue to red as you go out from the radii. That's the underlying scalar field. You take the derivative, what you get is a bunch of arrows, which is a vector field. That particular vector field is 2x, right? If I take the gradient of that vector field, so gradient of that vector field 2x, what would that be? Say that again. What was the gradient of the vector field x that we calculated last time, of the vector x? Yes, it was identity, right? So last time we showed that if the vector field is x, the gradient of that vector field turned out to be an identity tensor field, which means that a gradient of 2x would be twice identity, right? So what that means is you go to any point in this space, at that point there is a tensor which the value, quote unquote, value of that tensor is 2 identity, which means what? And a sphere, a blue ellipsoid that looks like a sphere of radius 2, right? And if you remember when we said that an identity tensor would take a sphere of arbitrary vectors, unit vectors, and take it to the exact same sphere. But 2 identity would just take it to twice as big a sphere, right? So you have to imagine what a tensor field looks like. It would look like spheres all over the space. At each and every point in this space, there is a scalar field which is denoted by color. At each and every point, there is a vector field, which is denoted by that arrow. At each and every point, there is a tensor field also now, which is denoted by that sphere of radius 2 in this particular case. So in the same way, you can, if you start out with some scalar field, you take first derivative or first gradient, that will give you a vector field. You take a gradient again, that will give you a tensor field. Okay. All right. So I'll let you look at the example, and now let's proceed further. So there is a nice analogy between these different vector products. We know that dot product, cross product, and the dyadic product between two vectors. The first one gives a scalar, the second gives a vector, the third gives a tensor, right? In the same way, these derivatives that we've talked about for the vector fields also have the same sort of analogy, that a dot product of the vector field V with the grad operator that I showed you gives me a scalar, right? V dot grad gives me a scalar, which is what we are calling divergence of a vector field. V cross grad cross product gives me curl, which is a vector field. V cross grad or V dyad grad gives me a tensor field. So you can see sort of a very nice analogy between the vector products and its 3 types of derivatives that we've talked about. An easy way to remember sort of that what do you get when we take a div or a curl or a grad of a vector field, okay? All right, very similar to what we had in scalars. In scalars, we had something called the directional derivative, right? Which measured that how does a scalar field change if I go in a particular direction. Gradient of a scalar field measured how the scalar field would change in all possible directions. But directional derivative told me that in a particular direction, how does the scalar field change? We have a similar concept in vector fields as well. if you are given a vector field, which is like a bunch of arrows in the space, if you are at some point x and you move in some direction n, then you can figure out how do the vectors change from this point x to another point x plus epsilon n. Okay, which is what this is, the definition here says, that find the vector field at a point x plus epsilon n, right, and subtract the vector field, the vector at the point at the position x, and take the limit with epsilon tending to 0. That, of course, is the same definition that we had for scalar fields, that take the derivative, the normal derivative with respect to epsilon of v plus x epsilon n, and it so happens that you can show that this directional derivative also follows the same logic, that you take the directional derivative is equal to the gradient of the vector field. So this guy, if you remember, we said that this was the gradient of the vector field acting on n. This is a tensor, that's why I have a tilde under this, and that tensor is going to act on n to give me the directional derivative of a vector field. Question: directional derivative of a vector field will be what? A scalar, a vector, or a tensor? A vector, right? Yeah, because indeed this is a tensor. Tensor acting on a vector should give me a vector. And since it is associated with each and every point in the space, it does give me a vector field. Let's take a couple of examples. For the particular vector field x, which we all know what it looks like, if I were to do the directional derivative for x in the direction x, basically what that means physically is I am at some point x in the space, and I am moving also in the direction of x. So my n in the first case is along the x direction. So I'll plot the x vector as well. That's the x vector. And in the first case, my n vector is along x. So if I do that, what we get is, from the definition, if Vx is defined as x, then directional derivative, the way that we write directional derivative is also important. We denote that with capital V. Directional derivative of the vector field V in the direction x is given as d over d epsilon of V of x plus epsilon n. Take the derivative first, and after taking the derivative, set epsilon equal to 0. That's the general definition that will always work for any type of directional derivative. Go ahead, Vikita.
I have this confusion about x, I think, since the last lecture, and I'm not able to understand when x is used as a variable and when it is used as a direction. Because when we say v is a function of x, I mean the vector v is a function of x. It means v is a function of x, which is a variable.
That's correct. X, which is a vector variable, yes. So here you see the way I'm writing it is that the vector field is a function of the vector variable x. What is the vector variable x? It is describing some point in space. So I have e1, e2, e3, which let's say are the coordinate basis vectors for my space. I could have x as some point in my space, right? At that point x, I have some vector v, which is associated with that point. At a different point, so if I were to call a different point, let's say y, then there is a vector v associated, a different vector v associated with this point. So if you go to any point in the space, there is a vector v associated with it. That vector v is function of the position. In this particular case, when we say vector vx is the vector x itself, what this means is that instead of this vector, the vector x itself is the vector field at that point. So if you go to any point, for example, this guy, from that point, draw the exact same vector out, and that is the vector field x. So I'm not sure if that answers your question. Okay. Okay. So the directional derivative of the vector field, we all know how to take derivatives with respect to a scalar. So no matter what is inside here, this derivative we can always take. In this particular case, what is the derivative of, so I'll write this actually again, derivative of with respect to epsilon x plus, this is x plus epsilon n, and in this particular case n is also x, right? So usually when we have in this point we are saying that the directional derivative of v in the direction n is what we want to find. So when n is equal to x, what we get here is x plus epsilon x. Take the derivative first and then set epsilon equal to 0. What is the derivative of the vector x with respect to epsilon? 0. X does not depend upon epsilon. And 0 vector, I'll call it to be consistent. X does not depend upon epsilon, but we do have an epsilon here. Derivative of epsilon with itself is d epsilon is 1 indeed. And what we get as a result is that we get x in the limit epsilon tending to 0. Since this does not depend upon epsilon at all, this is not needed. And what we get is that d of the vector field x in the direction x is just x. So the first one here turns out to be just x. The second one is what I'm saying, that what is the derivative of the vector field x? We know what that field looks like, just arrows pointing radially outwards. What is the directional derivative of that vector field in the direction x perpendicular? What is x perpendicular? It's some variable, it's some vector that is perpendicular to x. So let me show you what that means. I was showing you this vector field. X perpendicular would be this, a unit vector perpendicular to x. Okay. So in that case, I would still take the derivatives exactly the same way. D of v in the direction x perpendicular would be equal to d by d epsilon of x plus epsilon x perpendicular, and after taking the derivative, set that equal to 0. Again, the first one does not depend upon epsilon, the second one does, and what we get is x perpendicular. So, which is also not a surprise, because okay, let me write that first here. We are saying that the vector field x, that which was the original vector field we had, we are trying to find the directional derivative of that vector field in any possible direction, where that direction that I'm talking about could be n, could be any direction. In particular, if I chose n equal to x, what I got was that the directional derivative of this vector field is x itself. Now, is there a way to verify this without using this directional derivative formula? Yes, so indeed we said that the directional derivative of v can also be calculated by taking the gradient of v acting on n. What is the gradient of this particular field? Identity. Identity acting on n will just give me n. So if I choose n equal to x, I get x. If I choose n equal to x perpendicular, I get x perpendicular. Okay. Um, so basically, in all, what we have for vectors are these four types of derivatives: divergence, third, gradient. Each of them result in a scalar field, a vector field, and a tensor field. And then this fourth derivative, which is a directional derivative of the vector field itself, which also gives me a vector field. Um, All right, and actually this directional derivative you can think of as a special case of the gradient or the grad derivative, because we are taking the gradient in a particular direction, which is what directional derivative is. All right, so let's take a look at tensor fields. We've done scalar fields, vector fields. Let's take a look at tensor fields. First of all, what does a tensor field even look like? As I pointed out a little while ago, it looks like a bunch of ellipsoids at each point in the space. Just like a scalar field looks like a color at each point in space, vector field looks like an arrow at each point in space. A tensor field looks like a bunch of ellipsoids, each ellipsoid attached to each individual point. So you can imagine, obviously, this looks like a discrete set of ellipsoids. It's not really discrete. If I have some body that it has infinitely many points. If I go to a point, I can visualize a tensor at that point as an ellipsoid at that point. The very quote unquote next point, there is no such thing. But if you think of a point, a neighboring point, it also has an ellipsoid which overlaps with the ellipsoid from the other point. So there are infinitely many points in space, and each point is associated with a unique ellipsoid of its own. That's what a tensor field looks like. Or you can think of a jar of M&Ms. That's also a tensor field. Okay, so here's an example of a particular tensor field. So this tensor field is a function of x. So if you change x, the tensor at that point will change. We are defining it as some scalar, which is x dot x, which is just that if you start from the origin, go to some point, that's the magnitude or the square of the magnitude of that position vector at that point. That's x dot x. And you take that scalar and multiply that with an identity tensor. What does that look like? So let me ask you this. If I neglected this other term, let's not think about that just yet. What does this term alone, quote unquote, look like? What would that tensor field look like? X dot x times I. That's right. So x dot x indeed is the square of the magnitude, and identity is a sphere, right? So at origin, what does the tensor look like? Radius 0 actually, right? At origin, the x is 0. So at origin, there is no sphere, it's a dot really. But as you go out, as your radius increases, then the magnitude of or the radius of that sphere also keeps on increasing. It increases at the rate x or r square as the distance r from the origin increases. So that's what that particular tensor field would look like. Small spheres near the origin, very large spheres away from the origin. Minus 2x dyad x. So this is a funny tensor, but let me see if I can, or if you can visualize this particular tensor. What do you think x dyad x would look like? So let's pick a point. In fact, if I have E1, E2, E3, I'm saying that go to some point x, and there is some ellipsoid out there that I want to figure out what it looks like. So if I'm talking about a tensor x dyad x, what does that look like? How do you even determine what it looks like? How do we determine what any tensor looks like? Yes, that's one way. We can find out the eigenvectors and eigenvalues of this particular tensor, and you'll see that two of them are 0. And the reason here is that, so indeed, that is one way of visualizing it. But another way of visualizing what any tensor looks like is just take that tensor, apply it to an arbitrary vector, some vector u here. What would the result be in this particular case? Okay, very good. So yeah, x dot u in the direction x. What this tensor does to any arbitrary vector is it always, so if I have some arbitrary vector u here, this particular tensor will take that arbitrary vector, dot product it with this x, you'll get some scalar, and it will take that scalar and put the result in the direction x itself, right? So no matter what vector u you give to that tensor, this particular tensor takes that and just switches its direction to x, and of course scales it by x dot u. So what does this tensor look like? Say again? It does indeed. It's an ellipsoid, a degenerate ellipsoid where the other two dimensions are 0. It looks like a line or a arrow along the x direction. Okay, so in general, a tensor which does not have two eigenvalues 0, it looks like a nice ellipsoid where you have three major and minor axes. In this particular case, this is a special tensor where the result always is in the direction x, no matter what vector u you give it, and therefore it will what this particular tensor looks like is like a thin needle out here. We already said that this part of the tensor is a growing set of spheres. This part of the tensor is a thin needle along x. So when you add them together, it kind of takes that tensor and flips the direction of some of them. Okay, and actually we'll show later on that this is actually a reflection tensor where reflection is being done on a plane perpendicular to x. So we'll get to that, but okay. So this is an example of a tensor field. It could be some weird complicated function of x, but the idea here is that another thing to note here is that this tx may be some non-linear function of x, right? X dot x clearly non-linear, but its operation on an arbitrary vector u is still linear. When I calculate t acting on u, that is always linear. Okay, that's a tensor is a linear operator. So even though tensor is could be a possibly non-linear function of x, t does not act upon x. T is only a function of the position, and t will act on u, some other vector also at that position. All right, so that's kind of a quick introduction to what a tensor field might look like. Let's take a look at some derivatives of tensor fields now. And believe me, we will use this derivative, divergence of a tensor, very often going forward in chapters 2 and 3. All right, so what does that divergence look like? this hopefully should look familiar to you now. This is nothing but the flux of a function divided by the measure of a infinitesimal body with the limit tending to 0. That's the definition of the derivative. It is the same definition that we used to define divergence, curl, and gradient of a vector field also. Right? So that's how general and how powerful really this definition is using fluxes. Um, let's see, what else do I want to say here? In terms of components, what it looks like is you take the partial derivative of t with respect to xi out here. So for example, I have this as the tensor definition. We'll do that as an example. So in order to do that, we can express partial xi. I will express t as t of mn e sub m dyad e sub n, right? I can write a tensor t in this format using its components. Does that make sense? You remember that we said t is equal to t mn e m dyad en and ei finally out there. What would be the result of em dyad en acting on ei? It would indeed be the dot product of these two vectors, which in this case is delta ni. I can contract out n here with this n and replace that with I. Okay. Do I have too many i's here? No. Okay. So partial of t m I partial xi in the direction what? em. That would be the result of taking the divergence of a tensor t, and I'll do this with components first, and then I'll also show you in the matrix form what it looks like. Is there a shorter way, yet another more shorter way than this to write this? Yeah, with a comma, exactly. So this is equal to T M I comma I E I. So when you see things like T M I comma I, that comma just means that I'm taking the partial derivative with respect to xi. Okay. Sorry, EM, not EI. And okay, let's take a look at this particular example that we were doing. For this particular tensor field, x dot x is xk. Identity tensor is delta ij ei dyad ej. I'll even place ei dyad ej in parentheses. And minus 2x dyad x is minus 2 xi ei xj ej, and a dyad between those two. Okay, so that's my definition of the tensor using components. To take the derivative here, what do I have to do? What do I have to do to take the derivative? Okay, first of all, what would be the result? In what direction would that result be? So if I have some tensor T where I called the components mn, the result was in the direction m, right? If I have a tensor which components has I and j, the result will be in the direction ei, right? Yeah, so indeed the results will be in the direction ei, and what I'll do is I'll do t m I comma I. So to do that, and actually I'll uh, use the partial derivatives just so that it doesn't get too so I'll put this EI way out here. Partial with respect to um, um, since I want partials with respect to J, so xj of xk delta ij, and then ei, the first ei, and then minus 2 times partial with respect to xj of xi xj. Do you agree that what I've written here is straight away from the definition of the divergence of a tensor field? That if the tensor had the components m mn, and actually I contracted n out with I, so if the components of the tensor were in mi, what I got was that the divergence would be tmi comma I, where I is repeated and m is repeated. So there are really 9 terms in here. So if I do that, the first question is this okay? How many i's and j's do I have here? It looks like in this particular term I have 2 k's, 2 j's, and 2 i's, but again I have 2 i's here, 2 j's here. Can I do that? I can do that because there is a minus sign here. These are 2 different terms. Okay, so and that's the note out here actually. But so when I take the first derivative, I'll break it up with product rule. I'll say it is partial xk partial xj, xk delta ij ei minus 2 times, oh, I need another term here, so plus xk partial xk delta partial xj times delta ij ei, and minus the same thing here, minus 2 times partial xi partial xj ei, and minus 2 times partial sorry, I'll write it in the next line, minus 2 times xi partial xj partial xj ei. Alright, let's take those partial derivatives now. What is the partial derivative of xk with respect to xj? Delta kj. So that's delta kj. Partial derivative again, x delta kj at this point, delta I with respect to delta j, delta ij. How about delta xj with respect to delta xj? Delta jj, which is 3, right? So I'll write delta jj for now. Let's see if we can contract out some things here. So indeed, for the first term we can contract out k. I'm left with j here, and I can also contract out this I have j here. So then the second term, again contracting out k, I have j, and contract out I have j, and this term j and j, we are left with I, and this will just be 3. So if I write out the result here, we would get xj ej plus xj ej minus 2xi ei minus 6 xi ei. And of course, if we cancel off this, this is just vector x, this is another vector x with this minus 2x, then the result is, oops, minus, oh. Not sure what happened there. Okay, so we have the result as minus 6x. Divergence of a tensor field gave me a vector field, right? Which is also expected here because tensor field acting on the vector n will give me some vector, integrate that over the area of the body, that will be a vector, divide that by some scalar volume, that will be a vector. So tensor divergence of a tensor field gives me back a vector field. Okay. One way to do this using components is as follows. So let's say in this particular case, I had this tensor. I'll take a simpler tensor field xi delta ij ei dyad ej. Only the first part of that tensor field is what I'm taking here. Can you, sorry, xk. Can you tell me in components, how would I write that? Yes, it would indeed be xk on the diagonals. And remember that xk is x1 plus x2 plus x3. It's the same quantity on the diagonals because this part is just identity. And the other part we had was minus 2x dyad x. How would you write minus 2 times x dyad x? Right, the components of this would just be xi ei dyad with xj ej. So the components would just be xi xj, which is what? Which is x1 x1. I think I'm going to need more space. x1 x2, x1 x3, x2 x1, x2 x2, x2 x3, x3 x1, x3 x2, x3 x3. In components, that's what it looks like. If I want to take divergence of this particular tensor in terms of components, it would be with some abuse of notation like this. T acting on the grad operator. Okay. So what is the grad operator? Basically, I can represent this with the components of T, and the grad operator would be partial x1, partial x2, partial x3. So if you combine all of that, you will get a 3x3 matrix of components, and you take that 3x3 matrix of components, act it on this quote unquote vector, and of course you take the derivatives just as usual, and I'll let you verify that when you take these derivatives of this particular tensor, that the result is minus 6x. So I'll let you verify that this turns out to be equal to minus 6 x1, x2, x3. Okay. Question?
Why did you take the derivative of xj on the previously?
So, using the component version? Okay. Here? So take a look at this. This is the definition, or in terms of components at least, for what a divergence of the tensor looks like. Divergence of tensor is T, M, I. Those are the two components. M, I are the components. Okay. So if my components are Ij, for example, in this case, my components were Ij. Okay. So the derivative is supposed to be with the second component. So since j is the second component, I take derivatives with j, and the result is in the first component, in the direction of the first component, which is ei here. Okay. All right. So question.
When it x diag x product, how is that in the next?
X diad x. Oh, here.
Yes.
So x diad x is nothing but xi ei diad with xj ej, right?
But it has to act on something like x diag x.
No, it's a tensor. X diad x is a tensor, right? So this is a tensor, which basically I'm writing as this is a vector x, this is a vector x. I'm taking a dyad product between them. The result will be a tensor. So I can pull out x. Okay, let me write this part again. What this would be xi, xj, and ei dyad ej. So xi, xj is these 9 terms, right? Okay, all right. So I have we have done all the derivatives, but we have not done the integral theorems, which will not allow you to do problem 3 of the homework 3 just yet. So we'll still stick to it. I think on Friday, the first thing I'll do is finish this off, and then we'll start chapter 2 from the following Monday. Okay.